Okay, evaluate the following limit or state that it doesn't exist. Okay, so as x approaches 1, I can see that in the numerator, as x approaches 1, I get 0, and in the denominator, as x approaches 1, I also get 0. So this is an indeterminate form of type 0 over 0, so we can apply L'Hopital rule. So this is equal to the limit as x approaches 1 of the derivative of the top, which will be 4x cubed, divided by the derivative of the bottom, which will be 3x squared. Now, as x approaches 1, the bottom is not 0 anymore, so I can just go ahead and plug in 1. So this will give me 4/3. For the next one, I want to compute the derivative. So it's 2 to the x times natural log of x squared. So dy dx, I'm going to need to use the product rule in combination with the chain rule. So for the product rule, the derivative of 2 to the x is going to be 2 to the x natural log 2 times, I'm going to leave the second one alone, plus, now I'm going to leave the first one alone and take the derivative of the second. The derivative of natural log is 1 over, I'll leave the inside function alone, times the derivative of the inside function, which will be 2x. And I'd leave it just like that. The next one, I have theta equals sine inverse of square root of x. Find d theta dx in terms of x only. Okay, so what we'll need to do is I need to know the derivative rule for the derivative of sine inverse. So probably that should be something that you put on your note card. So take a look at that. Okay, it is 1 over the square root of 1 minus the inside part squared. The inside part is square root of x, so it will look like that. And then times, now I want to take the derivative of the inside part. The inside part is square root of x, which is x to the 1/2, so I can say that that's 1/2 x to the 1/2 minus 1. Okay, here I have the graph of a function v of t is given below. The function v represents the vertical velocity of a car on a roller coaster in terms of the number of seconds elapsed since the roller coaster started moving. At the beginning of the ride, the car is 20 meters above the ground. Okay, so then it says, how high does the car climb in the first 3 seconds of the ride? Okay, so in the first 3 seconds of the ride, I'm going to be looking at this area under the curve here. So that will be the integral of v of t dt from 0 to 3. And that will tell me the vertical distance traveled. So I just need to compute the area of that triangle. So that'll be 1/2 times the base times the height, which is just 3. The units of that are, the velocity is in meters per second, so 3 meters. What is the car's height at 6 seconds? So to find the height of the car at 6 seconds, I need to figure out, I can do the integral from 0 to 6 of v of t dt will tell me how much the height has changed. So this would be the change in height in the first 6 seconds. So if I compute all of those areas, I'm going to get the 3 from that first triangle, plus I'll have this rectangle, which has base 1 and height 2, and then this will be half of one of those, and then this will be a -1. So if we just compute the areas of those triangles and rectangles and add them up, we should get 5. And we know that at time 0, it was 20 meters above the ground, so it should be 20 plus the change, So 25 meters should be the answer on this one. For what value of t is the height of the car minimized? Okay, so I know that the height, that the velocity, the vertical velocity, is the derivative of the height. So I can use the first derivative test. So if I have my v of t, which is the derivative of the position, s prime of t, the velocity is 0 at certain points here and here at 5 and 8. In between 5 and 8, the velocity is negative. Before 5, the velocity is positive. And after 8, the velocity is positive. So that means that my position is increasing, and then my position is decreasing, and then my position is increasing. So the height of the car should be minimized at 8 seconds. And this is by the first derivative test. What is the car's acceleration at t equals 9? So I know the acceleration is the derivative of velocity. So at 9 seconds, I want to know the slope. So if I go over 1, I go up 1, so the slope is 1. So the units of velocity will be meters per second squared, or meters per second. So for the next one, it asks to find dy dx for this implicitly defined curve. So I'm going to take the derivative implicitly with respect to x. So the derivative of so let me write it out over here. So I have e to the y minus x cubed equals x cotangent of y squared. Okay, so, all right, so the first part, the derivative of e to the y with respect to x will be e to the y, and then the derivative of the y with respect to x will be dy dx. Minus the derivative of x cubed with respect to x will be 3x squared equals, on the right hand side, notice that we have the product of two functions, so I'll have to use the product rule. The derivative of x with respect to x is 1, and I'll leave the second function alone. Plus, now I'm going to leave the x alone. The derivative of cotangent is negative cosecant squared, so cosecant squared, but it's negative, so that will change this sign to a negative. I'll leave the inside part alone. Now I'll take the derivative of the inside part, which would be 2y, and then the derivative of the y itself will be dy dx. Okay, and so next I need to, the terms that have the dy dx in them, that's here and here, I want to get those two terms on the same side. And the terms that don't have dy dx, I'll add or subtract to get them onto the other side. And so I'll have e to the y. I'll have e to the y dy dx plus x cosecant squared y squared 2y dy dx equals cotangent y squared plus 3x squared. Now I can factor out the dy dx and divide by the leftover stuff. So I'll get dy dx is equal to cotangent of y squared plus 3x squared divided by e to the y plus x cosecant squared y squared times 2y. So that's your final answer. For the next one, I'm told that a hot air balloon is rising straight up from a field, tracked by a rangefinder 500 feet from the liftoff point. So I can see that this 500 is labeled there because that is a quantity that is not changing, so we can label that with a numerical value. At the moment, the rangefinder's elevation is pi over 4 radians. The angle is increasing at a rate of 0.14 radians per minute. So I can see that angle is labeled with a theta there. So that means that d theta dt is given as 0.14 radians per minute when theta equals pi over 4. Okay. And I'm asked to find how fast the hot air balloon is rising. So I want to find dH dt. So in order to find dH dt, I need to start with the relationship between h and theta, and then I'll take the derivative implicitly with respect to t. So when I look back to my picture, how are h and theta related to one another? So I can see that tangent of theta is equal to h over 500. And so now I can take the derivative of that implicitly with respect to t. So the derivative of tangent is secant squared theta d theta dt is equal to 1 over 500 dH dt. Okay, and now what I want to do is plug in the values that I have. So that'll be secant squared of pi over 4. D theta dt I know is 0.14, and that equals 1 over 500 dH dt. So that gives me 500 secant squared pi over 4 times 0.14 is our dH dt. Okay, let's try to find a numerical value for that. So that when I type that into my calculator, I'm going to type in 500, and for the secant squared, I'll do 1 over cosine pi over 4, and then that whole thing squared times 0.14. Okay, so let's type this all in. Okay, so I got 140 for my final answer for that. And what are the units? So it is 500 feet and radians per minute. So this is feet per minute.